look at this section, um, which is the critical role of mass transfer in separation processes. Let's start by looking at what mass transfer is and how it's defined, which is basically the net movement of mass from one location, which is usually a region of higher concentration, to another of low concentration. And if our separation processes being basically a method which converts a mixture of substances into two or more distinct product mixtures, and one of which will be rich in one of the constituents. So, what drives this mass transfer? We need a chemical potential gradient, and this is normally our concentration gradient, and it's what will be used in most of the applications you would see in this course. So, as already alluded there, we are saying things naturally move from high concentration to a region of low concentration until equilibrium is reached. So why is it important? This is important. It enables us to make sure that we achieve the required product impurity through isolation of the final product. We look at our environmental sustainability. Processes results in harmful pollutants, which will be in the waste streams. So those needs to be removed before the gaseous and liquid effluents enter air or water. Then resource recovery. We are looking at our catalysts. We are looking at our solvents. We are looking at expensive unreacted raw materials that would require reuse. And for that to happen, since they will be in a mixture, mass transfer has to be employed. Feedstock purification. Here we are saying there are certain impurities in our feedstock that affects one, the rate of reaction, the yield. So by removing these impurities, we are reducing the chances of us there having side reactions that can even disturb the yield. We are removing impurities that have ability to poison our catalyst and threatening catalyst integrity and overall process efficiency. So industrial applications. So what we are saying, let's understand that a chemical plant is basically a reactor surrounded by separation equipment. So as indicated in Fig 1.1, there you would find that the reactor is at the heart. The reactor is at the heart of our process, and our raw material before they get to the reactor, impurities has to be removed. And when the reaction is okayed, gaseous stream needs to pass through separation processes for resource recovery and removal of some pollutants that are dangerous to the environment. The same applies to our liquid effluent, where we also need to employ separation to remove some of the harmful substances in our liquid effluent stream before it goes to its sink, which is maybe the water bodies or land. as might be. Then finally, our liquid product there is a mixture of unreacted reactants, products of side reaction, and the main product. So we need to employ separation so that we recycle the unreacted raw materials, and that's employed mainly if they're expensive raw materials in most cases. We need to also employ separation so that we achieve the product purity that we require there. So continuing with our industrial applications there, where we are saying where are we applying product purification and recovery? Look at your pharmaceuticals, where we extract active drug ingredients from fermentation broth, which requires about 99% purity is a requirement for patient safety. Petrochemicals, there you can think about your crude oil separation into fractions, your LPG, gasoline, jet fuel, asphalt, food and beverages. The application there, an example could be you caffeinating your coffee there, concentration fruit juices, as you can look at, making of your wines, your spirits, as you can see. Then, as we continue again with that, we look at us protecting our environment, air pollution control. We are making use of scrubbing to remove your SO2, your ammonia from factory smoke, water treatment, desalination, where we are making use of reverse osmosis to produce drinking water from the salty water from the sea, wastewater, employing activated carbon to trap toxic organics. Then we also look at the biological and healthy system. So it's important to note that mass transfer is essential for life itself. Why? So if you look at the respiratory system, we breathe in air, which is a mixture of our carbon, our nitrogen, carbon dioxide, and oxygen. Of importance, there is our oxygen that needs to get into the bloodstream, and after use, it also needs to be expelled from the system as it moves from blood to air. As you can see them, then we can look at the advances in medicine, where we talk about the kidney dialysis for those who have issues and challenges with their kidneys, so that we remove urea from the blood while keeping essential proteins there. As can be seen there, we can also talk about drug delivery, which has allowed advances. So the energy challenge, the most difficult issue with this is our energy demand that is posed by separation processes. So understand that 10 to 15% of world's energy consumption is through these separation processes. So what does that mean? We are saying that we need to look at seeing that we move from thermal processes, which is distillation, which is the most common separation process employed by the industry, by the industry there, as can be seen there. This is moving to right, as can be seen there, to non-thermal processes where the advances in membranes is coming to play. The carbon capture and sequestration, where we are looking at developing better solvents to absorb CO2 from the atmosphere. So, in conclusion, it's important that as a chemical and process systems engineer, you have sound knowledge and expertise in separation methods as you do your day-to-day functions as an engineer. So we are saying these processes form operational backbone of the chemical and petrochemical industries, detecting the viability of entire. So